Ditto.
Well, cool. 11 past 11. So let's get started. Today we have lecture 17, the second part of the parallel machine learning classes, lectures. And we'll talk about unsupervised and semi-supervised learning today. This is a significant extension of lectures from the previous years, which used to be only about 30 minutes. And then the rest of the lecture, we talked about graph partitioning. We moved the graph partitioning to a completely different week, and it's going to be part of the load balancing and graph partitioning lectures now. So we have much more room here. But before I get into technicals, why don't we hear some announcements from Julia?
Yes, so we have three announcements, and the first is that, as you might read on the Piazza post, homework 2 part 3 has been the deadline has been extended until Sunday at midnight instead of Thursday. So you have 3 extra days. And then homework 3 is going to be released on Thursday. So you will have a few days of overlap. And then the deadline is also being extended to April 4th instead of the 1st. And the last thing is that this Friday from 1 to 2, there will be the lab 3 about UPC++ and genome assembly. So you should find be able to find a link on Piazza.
Cool, thanks, Julia. And if you haven't noticed, homework 2.3 deadline has been extended. Alok reminds me. So I suspect you know it, but just in case. Let's get back to the lecture. This is the outline. The top line is what you already covered last Thursday. And today we're going to cover these 4 topics. The second and third topics, depending on who you ask, are the same thing. And we're going to mention it when the time comes. And the last topic, you can use it actually, semi-supervised, supervised, and unsupervised. But I chose it as the exemplar of semi-supervised learning because it's the most common application of graph neural networks. Reminder of our bipartite diagram about a lot of machine learning methods being dependent on matrix algebra. And this is just repetition of what we've already seen. And today in this picture, actually, we're going to see a good coverage of things. We're going to see MCL and spectral clustering from the clustering domain, graph neural networks. We're going to see non-negative matrix factorization. So we're going to have a good coverage of these today. Clustering, as one of my colleagues once infamously said, the algorithm for this is dime a dozen. That doesn't mean they're bad. They actually have a lot of good uses. The data usually necessitates different approaches. So that's why there's so many different clustering algorithms. And you have to usually understand your domain to find the right kind of data. And what do I mean with that? If your data already comes as some sort of connected structure, then you can use graph clustering algorithms. If your data comes in a spatial embedding, then a lot of things like k-means are naturally meaningful. And if you have a concept of a density, then all these density-based clustering methods start making sense. And there are ways to convert one problem into another. If your data is not in the space, d-dimensional space, you think you cannot apply something like k-means, you can actually embed your problem into a d-dimensional space and then call k-means, and which is actually the first algorithm we're going to see. So, which is spectral clustering. The input, I say similarities between data points, this can be given to you. You have a lot of data points and some notion of similarity between them. And either you can construct that similarity by using many of these things listed in the slide, cosine similarity, Jacquard index. It usually depends on your data, which one makes sense. Or it can come as part of the input. Then imagine you have described this relationship between data points inferred by the similarities as a graph. And the weights of the edges is really that similarity you just either computed or took. You can define this graph several different ways in the literature. The most obvious one is the last one, fully connected. Just keep every single edge between every single pair of points. that usually is prohibitive from a computational perspective. So I don't, actually, how can I pin myself? Okay. So that in my recording includes me. Sorry about that. It's usually prohibitive to work on fully connected graphs due to the storage and computational costs. The two alternatives that are commonly used is epsilon neighborhood, in which case we identify an actual value and say that if the edge similarity is higher than that value, I'm going to keep it, otherwise I won't. This has the benefit of being geometrically meaningful. However, it has the downside that you can actually get disconnected graphs, significantly disconnected graphs, depending on how the similarities are normalized. The k-nearest neighbors, by definition, will avoid discontinuity because for each node, you're going to choose the kth smallest or largest similarities around it as its neighborhood. So you're almost guaranteed to have a connected graph, but then you lose some of the geometric meaningfulness of the data. So that's, you have formed your graph from your data, or your graph was given with any of these two methods. Then we go into the intuition of spectral clustering. It comes from the minimum cut. You can technically recursively partition your data by identifying a minimum cut, removing those edges on the minimum cut, and repeat until clusters are identified. Finding minimum cuts are not exactly easy. So the common approximation is based on this thing called the graph Laplacian. And this really is the heart of spectral clustering, as well as some spectral embeddings we're going to see in about 10 to 15 minutes. There are a couple different ways of defining a graph Laplacian, but the two most popular ways are unnormalized graph Laplacian, where you have a diagonal D, which describes the degree of each vertex. So it's this D matrix is in location dii, has the degree of the ith vertex. And W is just the -1s for each edge that are present. That's naturally not a diagonal matrix. And you get this thing at the bottom. This is the unnormalized Laplacian. What you can see in the unnormalized Laplacian on the bottom is every single column will add to 0 if you sum them up. And that's going to be useful in a minute. The normalized graph Laplacian, basically, you can define it two different ways, either symmetrically or based on random walks. The symmetric one I really like because it has certain benefits, and it is actually defines an eigensystem that is easier to solve. And that's just basically scaling the Laplacian on both ends with the square root of the diagonal matrix. So it's normalizing both ends. I recommend using that in practice because, as I said, this will involve solving an eigensystem, and it's easier when you have a normalized symmetric Laplacian. So here's how it goes. You construct a similarity graph from one of the methods we described. Then we compute k smallest eigenvectors of this matrix LSIM, and you stack these vectors on a matrix U. Now, what do we get? And then we normalize them, of course. We have an embedding simply. We started with an adjacency matrix or in a graph or some data that we constructed the similarity graph from, and we converted that into a matrix of dimensions n by k, where n is the number of nodes, and the k is the dimension we chose. And each one of these columns in that matrix is one eigenvector. So simply, this is converting your data that is in graph form into an embedding in k-dimensional space. And then you'll see why this is related to embeddings and dimensionality reduction, to be honest. But we're in the clustering section. So what do we do with that embeddings? Then we just apply a known clustering algorithm that works in the dimensional space, like a k-means algorithm. Why does this work? Well, it's beyond the scope of this lecture, but let's give the one very simple intuition. Think about this unnormalized Laplacian and you have your ideal case where your data points are completely disconnected from each other. So your clusters are very well identified. You just want the connected components of it. And each one of these connected components are well connected, let's say. So they are really good clusters. Well, my system, the smallest eigenvalue is 0. It cannot be smaller than that. And you'll see that this is the Laplacian, the unnormalized Laplacian. There will be blocks, each representing one connected component, however the value is, and there will be no edges across blocks because those are across connected components. So if my smallest eigenvalue is 0, then that means the vector I'm looking for is something that will give 0 when multiplied with this Laplacian. And you'll see that there's exactly k such, or let's not use the k, c such vectors, if c is the number of connected components. And each one of them looks like this. There's a 1 for the nodes that are part of that connected component and 0 elsewhere. And the next eigenvector is exactly like that, except that this for the different connected component. And if you multiply this, you'll see that this gives you a 0 value. So the multiplicity of the eigenvalue 0, the smallest one, is the number of clusters, and each one of these eigenvectors correspond to 1 cluster. That's the ideal case. Of course, in reality, you're not going to get these perfect disconnected clusters. There'll be edges in between, but this is going to be an approximation, and then the output will be still clusterable in this k-dimensional space you just embedded it. Okay, this is a parallel computing class. So which means, how do you solve this in parallel? There is the number one thing to identify is to go back to the beginning of this lecture where we find the workhorses of these algorithms. And it depends on what algorithm you use to solve this eigensystem. The commonly used solution is, for example, Lanczos algorithm that works on symmetric inputs, which is based on sparse matrix vector multiply and of course normalizations and so on. The problem with, and Lanczos algorithm converges really beautifully. The downside there is the workhorse is sparse matrix vector multiply, which has no or minimal data reuse. If you remember that sparse matrix vector multiply will touch every data point once and do only 2 floating point operations for that. So it doesn't have reuse, and it's hard to scale, and it's not a great fit for the architectures we have. Alternative algorithms are possible. Power iteration is still sparse matrix vector multiply, so I'm not going to talk too much about it. But something worth mentioning is LOPCG, locally optimized block conjugate gradient, precondition called conjugate gradient, a mouthful. But think of this as iterating over a much larger subspace as opposed to Lanczos, which explores one Krylov subspace at a time. This one explores them in bulk. So you get this block version in some sense. It is not as, it doesn't converge as fast as Lanczos if you think about the overall work that's done. But since the fundamental operation becomes a sparse matrix times multiple vectors, or sparse matrix times tall skinny dense matrix, then you get better scalability. So you trade off these two things that, okay, it converges a little slower, but you get so much better utilization in current architectures and better parallelism that there, in many cases, the LOPCG becomes a faster solution. In the end, if you want to implement spectral clustering, you probably just want to call something existing, some existing software. And that means you're going to use, for example, ARPAC, which is how to describe these tools. These tools are called reverse communication solvers, meaning the ARPAC implements the high-level algorithm logic for eigensolvers. PARPAC is parallel version of it. And your job is to implement the SPMV and other primitives within it. And this gives you the flexibility. You say that, okay, I don't understand solving eigensystem, all the numerical intricacies that comes with it. And I don't need to understand it. All I need to know is match the SPMV, for example, in my architecture, GPU, distributed machine, as much as possible. So I just implement the functions that ARPAC or PIRPAC calls. And then the PIRPAC or ARPAC will handle the numerical part for me. So that's one way of designing an algorithm, designing a library, sorry. Cool. I see that the question has been answered by Olaf. Thank you. Okay. Let's continue. This is the second clustering algorithm we're going to talk about. In case you wonder why this lecture is called unsupervised learning, it means that we don't have training data. We only have data that has no labels, and our job is to make sense of that data. And the clustering is one way to make sense of data, to just put together things that seem closely related to each other, but loosely related to the rest of the data. Right? We've seen spectral clustering, which does this through eigen space embeddings. And the macro cluster algorithm is a fundamental different one. That one is based on random walks. The algorithm inventors call it based on flows, but you can interpret it either way. So this is related to something else we're going to see later in the class, which is two nodes or data points are connected to each other if they are co-occur in a random walk. And that's one way to describe it. So, but probably an easier way to understand macro cluster algorithm is to think about this as a graph, as input as a graph. Each data node is a sample, and edges are similarities again, just like in the spectral clustering sense. And if I start randomly walking on a node, I will most likely get trapped within a well-defined cluster. Then just jump to a different cluster. But that's just based on pure probability. So how can I use that information to design an algorithm that's going to pop out the clusters? Well, I'm just going to start random walk from every single vertex, all at the same time. The problem with that approach is at some point, I have to dampen the low probability paths, because otherwise, if I just blindly do random walks, I will eventually reach to anything that is connected to me. And on a connected graph, it will be all the other vertices. So that's just going to become intractable computationally, and it's not going to give me two meaningful clusters. So I want to reach other vertices from random walks, but also cut the edges that are low probability. So how can I do that? I do iterate between two steps called expansion and inflation. Expansion is taking basically one step of a walk in a graph. So every vertex just tries to reach to its neighbors. And then inflation dampens the low values to 0 and amplifies, relatively speaking, to higher values to higher things. So how does that work? In the inflation case, imagine you have a column of this matrix. And let's look at this. This is not a good picture to look at. I'm going to come back to the inflation, and it's going to become much easier to explain there. Let's start with expansion then. How do I take one step of a random walk from every vertex? I just square the matrix. So why does squaring achieve what we hope that it achieves? Well, simply what we get is, if I square, just look at what happens in one column of the output. One column of the right-hand side matrix is just the adjacencies for that vertex. Now imagine just the first column here. These means that this vertex is neighbors of 1 and 3. And in the output, the same column of the first column will involve the neighbors of neighbors. So I expanded my neighborhood by making my neighbors of neighbors my immediate neighbors. So I took one step further in the random walk. And that's why just squaring the matrix allows you to expand your random walk by one step. Okay, then how do I sparsify this thing to make sure that I see the clusters after several iterations? I can prune by using a cutoff in a certain value. Or there's other techniques that are like k nearest neighbors. I can just say, I'm going to only keep the k top entries in each column. But the actual thing that allows me to prune entries is inflation. Now, at every stage, we're making this matrix column stochastic, meaning the sum of each entries in each column are 0. And think about the following situation, where I have weights that are 0.9, 0.1, 0.0, 0.5, 0.05, sorry. So I have a really large value and small values. But maybe my cutoff is not small enough. Maybe my cutoff of pruning connections is just 0.01. But if I inflate these values, inflation is just taking element-wise power of each element in the column and then renormalizing. So now what's going to happen is 0.8 will not go down so much. It's going to become 0.64. But things that are really small, like 0.1, now they will become really small because that's going to become 0.01. And 0.05 will become 0.025. In fact, one more 0. So the small entries will go down to 0 very quickly once we inflate and renormalize. And then they'll stay under the threshold for pruning and they'll disappear. So that allows them to get cut out of the graph. And eventually what we're going to get is this picture. At each iteration, first I'm doing random walks and I'll densify for a little bit. But since I'm doing this inflation, renormalization, and another expansion, eventually the edges across weakly connected clusters will be cut. And then I will be left with this graph where each connected component describes one cluster. So that's the goal of MCL. Let me see if there's a question. Got you, okay, that's beautiful. What is the parallelism available in this MCL? Well, the expansion step has a lot of parallelism because as we said, it does sparse matrix squaring. However, you cannot blindly perform sparse matrix squaring if you want to cluster really large scale data. Why? Imagine that you have a graph where each entry, each vertex is connected to 1,000 other entries. And this is a common case in the applications of MCL in biology. This is a very popular algorithm in biology, especially. Once you square it, if everything was randomly distributed, each column would have 1 million non-zeros in the A square. And in reality, it's even worse than that because things are not uniformly random distributed. So there are some columns that are really dense, and once you square them, they create really dense output. So I have no place to store A square in general, even if even though I'm going to prune it later and get something reasonably manageable in size, I cannot store the intermediate A square. So what HipMCL does, which is a high performance implementation of this macro cluster algorithm, MCL, is it says, okay, I'm going to form B columns of the output at a time. Very simple. And you can do that because each column of the output is in some sense independent from another in the formation. So I'm just going to choose B columns, immediately inflate and prune them. So I get some manageable memory budget under a manageable memory budget, and then do it for the next batch of columns. And given the input size, given the analysis performed by the algorithm, it can figure out how many entries will be in each column and set this batching parameter automatically. The larger the B, the more memory you use, but you get more parallelism, of course. The smaller B exposes less parallelism. And in the extreme case, you degenerate into sparse matrix, sparse vector multiply. But almost never happens. So we're in the sparse matrix land for pretty much all reasonable use cases of this algorithm. The initial version of this algorithm, HIP-MCL, used the sparse summa, which is a sparse version of the summa algorithm that Jim talked about. And later we have expanded this thing to use communication avoiding algorithms, which are 2.5D and 3D algorithms while still keeping the memory constrained nature of the process, meaning you only form certain columns at a time and automatically choose them. And you can read both of them in the citations that are described. The communication avoiding algorithm is significantly faster. So no surprise there. But it was actually better than even the theory suggested for various practical reasons related to sparsity. And the things that I'm not covering for this algorithm is the pruning step also involves choosing k-nearest neighbors for each vertex at each iteration. And that's translates into case selection that needs to be done for all the vertices. And we're going to cover some of the algorithms for selection, and including case selection in the sorting and searching lecture later in the class. There's a parallel pruning method, which is trivial. We're not going to talk about this. Connected components are required to convert the output of the converge matrix into something that we can interpret. Even though connected components is a fundamental graph algorithm, we won't cover how to do it in parallel this year, but there'll be lots of other interesting aspects of graph computations that are going to be covered in graph algorithms lecture. All right, if you care about scalability, you'll see that there's this is how it works in practice. I want to highlight something slightly intriguing here, which is we increase the number of nodes by a factor of 4, and we are able to get more than a factor of 4 decrease in running time for the parts where we're broadcasting the first matrix. And that's a little odd, but let me explain why this is happening. So this is the first matrix, A. We call this one as the second matrix, B, even though they are the same matrix. How can the cost of broadcast go down so much? Increase the number of processes by 4, but the runtime goes down by 5.7. It really has to do with the phase selection. So I said, even though I said that the columns of the output are independent in some sense, and we can form them in batches, still, for each formation, I need, in theory, all of A. In this picture, it might not look like we need all of A to form the shaded region of A square, but if B is sufficiently large, and we're talking about millions in practice, just forming the shaded region of A square, I need to access all of A. So what happens when I run this algorithm in 10 batches as opposed to 1 batch? Well, I am rebroadcasting A 10 times. So that's the cost of the batching that I haven't described before. And by increasing the process counts, I'm increasing the total aggregate memory. Thanks to that, I can lower the number of batches I choose. The algorithm will automatically lower that, and I will broadcast A fewer times. So that's how I get more than 4 times speed up in the A broadcast, because I'm broadcasting fewer times. So it sounds like a cheat, but it's not, because that's the upside of strong scaling. If you have more memory, you should use it to the extent possible. Any questions so far? Beyond the one that Alok answered? just write it in chat, and I have time today to, I think, go over them. The second part of the lectures is about dimensionality reduction. Again, another unsupervised learning technique where you can think of this problem as mapping your high dimensional data, and I'm using quotations here, into a low dimensional so-called manifold. You can think of it as a space, vector space, but it can be shaped awkwardly. It doesn't have to be linear. So the word manifold is usually a replacement to describe something that's locally linear. The data, when we say high dimensional, it might be obvious to you, right? Somebody might have collected 1 million features for each data sample, and you kind of look at it and say, clearly this data cannot be 1 million dimensional. Some of these features are correlated or redundant, and I'm going to do dimensionality reduction to get rid of all this correlated noise. But sometimes the high dimensionality might be perceived in the sense that there is no 1 million columns, but you have an image, you have a video, you have a text, and you assume that an image is high dimensional because it has 1 million pixels. And you know, each one of them has several different colors. So you can think of a lot of these complex data as high dimensional as well. So it doesn't have to be in, you know, Excel sheet with the 1 million columns. And the mapping of from high dimensions to low dimensions can be linear, like principal component analysis, and non-negative matrix factorization we're going to see, or non-linear, where you try to linearize locally and unfold this Swiss roll, which is this typical picture that you might see whenever you read about nonlinear dimensionality reduction. They say, assume that the data is lying on a nonlinear manifold, like curved like this. And of course, this is a really bad case for algorithms like PCA, and it's not going to map this into a low dimension in a nice way. But if you use some of these algorithms that are designed for this purpose, like isomap, you'll get this beautiful separation between data points. All right, I had to shut down my heater here. Let's talk about the most commonly used, commonly known algorithm, principal component analysis. It's likely that you heard about this. The goal is to find k unit vectors in a d-dimensional space. These are called principal components. And you want those components to satisfy two things. One is when you look at the data projected onto the direction of each one of these vectors, you want the variance to be maximized. So you want that vector to explain to you as much as possible about the data. And you want that ith vector to be orthogonal to all the previous vectors you have chosen. And that's basically the constraints you have for PCA. And you can compute PCA with some known algorithm that is called singular value decomposition. It's, I guess, a half a century old, very beautiful algorithm, which decomposes any rectangular matrix into this form where the left matrix is the left singular vectors, right matrix is the right singular vectors, and there's a diagonal matrix in the middle. And your principal components are just your left singular vectors here. And I don't think we talked about this algorithm in the dense linear algebra, but there's several parallelizations of this. I'm not going to talk about them today here. Instead, I'm going to talk about a different algorithm called non-negative matrix factorization. This one is more ill-defined than PCA. PCA defines what these vectors has to be in the sense that they have to explain the variance as much in an optimal way as much as possible. And they have to be orthogonal to the previous directions. NMF doesn't put all these constraints. All it says is, I want my data matrix A to be decomposed into two factors, W and H, and each one of them, the inner dimension of them needs to be K. So you specify the K, just like you would specify in PCA what the dimensionality has to be. You have to provide the dimensionality. But all I want from W and H is they want to approximate my A when multiplied in some norm. And this might change depending on who your application needs. And all the entries on W and H needs to be non-negative. So that's all there is. The name matrix factorization, you can argue that it's a misnomer because this is an approximation only. You're not really, A is not equal to WH, but that's something we accepted. Yes, t-SNE is included in the nonlinear case. And there's a long list of different nonlinear and linear dimensionality reduction algorithms. I suspect you can find lots of surveys on this. So from my Slack messages. And NMF is a family of methods, not just one algorithm. You can solve this problem, this optimization problem that's described on top, minimize the difference between A and WH in some norm using several different algorithms. A very commonly used algorithm is the alternatives updates. And the variations of this is alternative least squares, alternative non-negatively constrained least squares, and so on. But all of them look like this. Well, initialize one of the matrices. Let's say you initialize without loss of generalization H. Now, I have a fixed H, and I know the A. Now I can solve for W, right? Solve this equation for W, which is one unknown. Because otherwise, I don't know which one I'm going to solve. I have two unknowns and one known. So the way I achieve tractability, I fix one of them and solve for the other one. And now I use the solution in the step one, which is the new W, and I solve for H in the second equation, and I alternate between them. So as I said, there's variations of this, and you can read many algorithms on this. This is one example I put. It's not just a definitive citation, but it's one I found valuable. And this is obviously not the only way to solve it. You can use anything that allows you to solve an optimization problem like this, right? So you can solve stochastic gradient descent, solve NMF with stochastic gradient descent as well. And here's one good paper about it. But let's say I decided that alternating updates is a good framework for me. How do I parallelize it? Well, the main computation, if you look under the covers, is computing these products, HH transpose and AH transpose, whenever we're updating W, and whenever we're solving for W for a given H, and similar computations for the other direction, for a fixed W when I'm solving for H. And what do they look like? Well, W's and H's these are actually not that bad. These are tall, skinny, or short, fat matrices respectively. So these updates are not that expensive. The really expensive one is turns out to be the multiplication of the data matrix A with the tall, skinny factorization matrix, or the current position of the factorization matrix. Remember that H's and W's are changing at each iteration. So this is what it looks like. The second one especially. Nope, this is the update just. Let's look at the multiplication of AH that gives you the W. In many cases, the A will be sparse, but A can be dense as well if your data is dense. So the commonly used parallelization is, there are two approaches you can do. One of them is you can cut all of them in one dimension, meaning cut A by rows, cut H by rows, cut W by rows. H is put in the picture on top, but you should imagine it as if it's next to it. This is I find it, and a lot of authors find it much easier to follow when you put the right-hand side matrix on top, because it's scaling the columns of A. But really, you're multiplying A and H and writing the output to W. Uh-oh. All right, let's come back. And the two-dimensional decomposition of this input and W and H looks like the following. You divide A into N over PR and N over PR pieces. So you interpret your process grid as having two dimensions, PR by PC. And we've seen this before. We talked about this in distributed memory programming lecture, where we worked with communication subcommunicators and designed actually a two-dimensional sparse matrix matrix multiply. Here, the operation is a sparse matrix, tall, skinny, dense matrix multiplication. Or the other wording for that is sparse matrix times multiple vectors. And again, only when the data matrix is sparse. If the data matrix is dense, then you're dealing with dense matrix times tall, skinny, dense matrix. So it's depending on whether the input is sparse or not. And these are the two ways to partition and parallelize. Unsurprisingly, the 2D is usually better. And we're going to see more of this 2D algorithm later, because surprisingly or unsurprisingly, this will come out as the workhorse of some of the other machine learning problems, like graph neural network training. We'll see in a couple of minutes. Okay, so far we are here, which is actually a good place to be in terms of time. And we're going to move into embeddings. This is a word that you might hear a lot, especially for papers coming from industry. And we're going to see this. This is actually, let's move on to this. What is an embedding, right? An embedding is, I'm going to describe this in the context of graph embedding. Let's say, and the node embedding. Think of the following graph on the left. And this is not something that is friendly to machine learning software. I have a graph, but the machine learning software likes to work on vectors. For each entry, it wants to treat it as a vector and do some sort of decision and training on it. Well, how can I convert my nodes in the graph to vectors? Well, exactly the point of embedding. I want to encode the neighborhood of you, and occasionally in conjunction with what I already know about you, into a d-dimensional space. This is the embedding space, so that the similarity of you and we defined on the embedding space is close to what I described in the graph space. Like if they share a lot of neighbors together, then they're similar. Let's say that's how I define in the graph space. Then I want the distance in the embedding space to reflect that. And the distance between ZU and ZV vectors to be close if they share a lot of neighbors in the graph space. Now the little star on the bottom says, remember spectral clustering. The spectral clustering's conversion of the similarity graph into a matrix of k eigenvectors. That was an embedding. That was an embedding using the eigen decomposition. So that's not completely new here. Arguably, if you consider objects like graphs or texts or trees or DNA sequences as high dimensional, then this is also just dimensionality reduction in some sense. And there's a lot of methods that do embeddings, and there's a whole cottage industry of X2Vec, I call it, node to Vec, word to Vec, sequence to Vec, graph to Vec, and here's a beautiful picture from doc to Vec with contrastive learning, I guess. At the end of the day, all you're doing is converting your objects that you perceive to be high dimensional and unfriendly to machine learning software into vectors which are friendly to machine learning tools. Chat. Is this an alternative to representing graphs as sparse matrices? Significantly different, right? So graphs and sparse matrices are just data structure representations. And there is, if you ask a graph person how you represent your graph, they will, if it's a static graph, they will admit that it's compressed sparse rows, which is the most commonly used sparse matrix storage format. There is very little controversy around this. You're not really changing much there. It's just a data structure naming question. Here, you're actually doing some operation where you convert your graph where each row has a variable size entry because it's the degree of the node into a fixed size length vector. So there is more going on here. You're making the data friendly to the machine learning software for downstream applications. Okay, there's really two commonly used embedding methods. One is factorization-based embeddings. These are known as shallow embeddings. And two classes I'm going to describe is the one is based on eigenmaps, Laplacian eigenmaps. And the beautiful hint is you already know this. Spectral clustering is nothing but Laplacian eigenmaps plus k-means clustering. So remember, in spectral clustering part of the lecture, we embedded our graph that represents similarities into a k-dimensional eigenspace. And then on that space, with each column was an eigenvector, we did k-means clustering. Now don't do clustering. And all you did is you embedded your data to an eigenspace. So that's something you already know, and algorithms we already talked about. You can still use PRPAC or ARPAC or your favorite spectral embedding implementation. The second class of those are based on factorization, the explicit factorization, where you're minimizing, again, the difference between your input A, which is some normalized version of your adjacencies or similarities, with the factor matrices Z on some norm. I'm not defining what norm it is, so I just left it N. Often people add a regularization term to enforce certain properties, but that's not important. And sometimes constraints might be added in Z. That's also doesn't change the grand scheme of things. You can still use the parallelization techniques often from NMF. You can use alternating updates framework in general, or you can use stochastic gradient descent, which we know how to do from the previous ML lectures. And then you have all this selection of how do I synchronize my gradient updates from different processors. That's a whole different research field. We're not talking too much here, but we briefly covered them with the gossip protocols, asynchronous updates, or synchronous updates in the previous lecture. So moral of the story here is, well, you already know how to parallelize both of these factorization-based embedding methods from the clustering and dimensional reduction parts of the lecture. One thing to notice is these two factorization-based embeddings that are described in the slides are so-called transductive, meaning that you are given the whole data and you train on it, and then you can answer questions within the data. If somebody gives you a new sample that's not in the data, these methods are hard to generalize to the inductive setting where you have to answer those questions of previously unseen data. Okay, thank you, Alok, again. Side story is you can basically take any embedding or any factor matrix coming from dimensionality reduction and or embedding methods and just use it as input to many different clustering algorithms and get a different clustering. If so, that's a trick that you can use it whenever you need. The second class of embeddings, again, remember, I'm talking about them in the graph land here, is random walk-based ones. And this is following the same intuition that we've seen in HIP-MCL. If two vertices co-occur on a random walk, they're similar. That's basically the definition of random walk similarity. So how do I write this down as an optimization problem? I write this big loss function, which is inside there's this predicted probability of these two vertices co-occurring on random walks. And let's not worry about the details about this, but only see that there is an issue with this formula, which is there is a double nested loop. The outer summation is U in V, and then we look at the neighbors of V. But the worst thing is within that loop, there is the another N in V. So this loop is at least N squared, where N is the number of vertices, or V squared, to be more precise. And that's just too expensive for sparse graphs, which are almost every interesting graph. So how can I approximate this? There is a way to do that, which is based on so-called negative sampling. And this is a commonly used technique. I say commonly used, but its history is not that old. It got popularized, I think, within the last decade. When your data has orders of magnitude more negative samples, and in our specific case of graph embedding, those are the missing edges. The edges that are not there is much more because the graph is sparse than the positive samples, which are the edges that are there. So I don't want to sum over all n square. I just want to get some missing edges in my normalization term. So replace the normalization term at the bottom, the normalization sum, instead of doing it as a sum over all nodes, just do it as a sum over negative samples. So that's the general trick. And with a lot of math, you'll see that this is all about how do you generate random samples and how do you do random walks on the graph. We're not going to talk too much about these because you know how to do random walks on a graph, at least at a superficial level from the HipMCL part of the lectures. You can just do, if you're doing random walks in bulk across many different vertices, you can just do sparse matrix times sparse matrix, where the left sparse matrix is your input and the right one is your current set of things that you're starting a random walk from. And HipMCL slides already give you an idea how to do that. But I want to highlight one aspect from a popular embedding tool called PyTorch Big Graph, which is if you do the trick about creating negative samples is if you do it naively and try to generate them one at a time, just like SPMV has low arithmetic intensity, this operation has very low arithmetic intensity. And doing it on distributed memory means you're going to be bound by latency costs. So instead, PyTorch Big Graph developers identified this, and they do their negative edge generation in a batched way. So you do B source and destination entities, and you just create negative samples from all of them all at once. And why does this matter? This way you convert your operations that do not have any arithmetic intensity into something that involves matrix multiplies. You can see this batch matrix multiplies. So moral of the story is converting your operations into matrix multiplies still apply even in the industry setting. And this is the additional things that the PyTorch Big Graph people do. I want to go quickly because I want to get to graph neural networks, where they do two-dimensional decomposition of edges for regular edges, and for edges that have for nodes that are low degree, they call it with small cardinality. They don't partition in 2D, they just partition it in 1D. So they all make sense, right? So you want two-dimensional decomposition in general, but if you have low degree vertices, you don't need that. You can just get away with 1D. And there's several other tricks. It's a nice paper, but I don't have too much time. Let's go into the last part of the lecture. And I'm going to finish by saying embeddings are great. What we described so far, either based on factorization or random walks, are task independent, meaning the user gives the graph or the user gives the data on which some graph is generated using some similarity function. And then some embedding is generated using these random walks or factorization-based methods. The task is not defined. Whether we want to classify, whether we want to do regression is not defined. So we have no way to optimize the way we do embedding to the task. So that's the downside. We cannot automatically learn to improve the way we embed. That would require backpropagation. That would require backpropagating the error of the task we have at hand. And so that's why we're going to talk a little bit about graph neural networks. So we have 25 minutes. That's a good time to be in. Graph neural networks, we're going to see it in the context of semi-supervised learning, where we have certain subset of data labeled, and the majority of it is unlabeled. So let's see if I can directly go there. This is a misplaced slide that I wanted to be here. Semi-supervised learning, again, as I said, the majority of the data is unlabeled. And you might wonder, what is the benefit of adding that unlabeled part of the data? Why don't we just train on the small subset of labeled data and then just try to do inductive decision-making on the unlabeled part? It turns out the unlabeled data adds a lot of value, and this is significantly better than just training on the small training labeled data only. And there are various reasons that we're not going to talk too much here, but you can read the literature about it. And the commonly used algorithm for that used to be label propagation, where, and that's a general name, where you try to propagate the labels of the things you know to their neighbors in some matrix computational way. But the graph neural networks seem to be slowly replacing that. So GNNs are, or graph neural networks, are used throughout sciences and industry. In this slide, I only use the scientific motivation. Protein data transportation, you can think of your whole transportation networks of cars or trains as a network, and then do prediction on traffic delays. You can do prediction on blackouts. You can do discovery on materials. And one of the things that made graph neural networks really popular is high impact articles, like in Cell or Nature, where scientists have discovered new potent antibiotics, or they figured out they solved a long-standing problem in protein folding. And at the top level, the title reads like AI discovered new potent antibiotic, but if you read the fine print, it's a graph neural network at the bottom. So GNNs are finding success in many challenging scientific problems, is the one line summary of this. But if you go to industry, this is also very commonly used in recommender systems and knowledge graphs, which are things that tie into everything we know. So what can we do with a GNN is I have an input graph. I have some latent knowledge on this graph through GNN. And now I can do node classification. Or I can do graph classification by looking at all these latent embeddings of vertices all at once and decide on what that subgraph should be classified as. Or I can do link prediction. I can say, is there a link between this vertex and that vertex? And all three of them are very valid use cases. We use node classification, for example, in node classification is used a lot in semi-supervised learning settings where you don't have labels on certain nodes. Think about a social network, you don't have labels everybody. Graph classification is used in molecule discovery. Link prediction is used in transportation networks often, but many uses are interchangeable. So here's the issue of training a graph neural network compared to training a convolutional neural network that we have seen before. And in convolutional neural networks that are applied in typical inputs like a set of images, each one of the images that are passed through the system is independent. So I can just say, I'm going to get a batch of 500 images, run stochastic gradient descent, update my parameters, move on to the next batch of 500 images. Whereas if I'm doing node classification in graph neural networks, the nodes are connected to each other. So I can't just say I'm going to take 500 nodes out of a graph with millions of nodes, just train on it, and move to the next batch, because the batch I chose, this 500, depends on a lot of other nodes that I didn't choose to begin with. So I'm going to have to touch the other vertices during the training process anyway. So I'm not getting the benefits of computational reduction. Just by training on a small subset, I might end up having to touch all of the graph. And that is the tricky part of doing mini batch training on graph neural networks. So if I can find a way to efficiently do this mini batch training on graph neural networks, I would get some benefits. One of them is the faster convergence per epoch, because we know from experience that mini batch training converges faster than full batch training. However, because of the way the graphs are connected, since I'm touching the same graph over and over again, like I'm going to use my mini batch 0 and 1 to start my training, then I'm going to touch 2 and 3, because in 1 or 2 hops, they will be accessible to me. And the next time I'm starting a different mini batch on 2 and 3, I'm going to touch 0 and 1 again. So I lost all the performance benefits. So slower training per epoch, and it's not clear which one will be faster in practice in the long run. And here's a different way of describing this issue, where the images have no dependencies across them. I can just take half of it, train, and then move to the next half, and I'm not losing any performance here. Whereas on this graph, if I took the core, the black vertices, and I say I have a 3-layer GNN, 3-layer graph neural network, which is not that deep. It seems to be a typical depth. I'm going to touch a significantly larger portion of the graph than my mini batches, because I need to reach its neighbors, and then from there, its neighbors' neighbors, depending on how deep the neural network is. And we don't really know how to, so I can get around this thing by using certain algorithms that are based on neighborhood sampling. So instead of looking at all the vertices that are reachable by L hops from the black vertices, I can say, well, I want to subsample this neighborhood. Now, then the question becomes, what is the right sampling algorithm, and how does one efficiently implement this? So the rest of this lecture, on the 17 minutes I have, the methods I'm going to talk about avoid subsampling and thus training on full graph, on a full gradient descent, to avoid these issues. But we're going to use the communication avoiding algorithms framework to speed things up. And that's Alok, your TA's work from last year's supercomputing conference. So what's a graph convolution? A graph convolution simply is feature aggregation from your neighbors. This is semi-supervised learning, meaning some vertices has labels. And for those of nodes that do not have labels, you can use a randomly initialized vector often. And so at each step, each vertex looks at its neighborhood and the feature vectors of all the nodes around this neighborhood, and somehow combine them. And when I say somehow combine them, this is not all that complicated. You can use the very typical way of averaging your neighbors. Sum them up, divide by the number of neighbors. And that's, of course, already is implemented by default. If you multiply your sparse matrix A, which represents your graph neural network structures, with a tall skinny matrix, where each row is the feature vector of that matrix. Now imagine what's going on here. So the feature vector of V1 is this thing that starts from 3.2. That becomes the first row of H. V3's embedding before this convolution started is this vector that starts with 2.7. That's the third entry in this vector. And the fifth entry is that. So those are the neighbors of V6. When I multiply with A transpose with this dense matrix of the current state of embeddings of the feature vectors, what I get is the output a combination or summation of all the feature vectors of my neighbors. Now I can normalize this thing or divide it by the number of neighbors I had to get my next set of features. Or I can combine it with my existing features, which is often what's done, how it's done. Technically, you don't have to have a different combination step. You can implement it all in one step if you include the diagonals in your A transpose and treat them separately. But that's an implementation detail. So the long story short, graph convolution can be directly mapped into sparse matrix times tall, skinny, dense matrix, or multiple vectors. So you see that we have another use case of SPMM. And we're going to dive deeper a little bit in a couple of slides. I want to highlight that graph neural network is an umbrella term for any neural network that performs graph representation learning. And graph convolution is just one way to do that. And the other very popular method of doing this is graph attentions. And we're not going to talk about this today, maybe next year. So that's what it looks like on the network layers. You can imagine conceptually that at each layer, the neural network is passing through nodes, that there is this as many nodes in the neural networks as there are vertices in the graph at each layer, and the feature vectors that are attached to it changes across the as you pass data through the neural network. And that's really not that different from convolutional neural networks, where the feature dimension changes as you progress in the deep neural network, right? Initially, the number of channels might be 3, then it's 12, then it goes up and down depending on the problem you have at hand. It's not that different in graph neural networks, where the feature dimension increases or decreases depending on what the user wants to achieve. So that's the storyline. The memory requirements are a little tricky, and that's the one of the thorny issues of graph convolutional neural networks or general graph neural networks. Now, I have to keep track of the different embeddings at each layer while I'm doing forward pass, because I'm going to use them in the backward propagation. So let's say, for the sake of simplicity, F is the feature dimension length here, order F, and that's fixed throughout the layer. I said that it's going to change in general, but let's use the average to get a good sense of what's going on. So I have n nodes. F, each one of them has order F feature vector length, and I have a network of depth L, capital L. So then I need order n times F times L storage just to be able to train this thing. And this can get large. So that's why we're looking at this problem from the distributed memory parallelism perspective. And if you are good at calculus, and especially vector calculus, and apply the chain rule repeatedly, then you'll get that the forward propagation looks like this formula, where you have the adjacency matrix, the embeddings H, and some mixing matrix. This is a small channel mixing matrix, or feature mixing matrix, you can call it. Learnable, meaning this gets updated at each iteration. And the backward propagation kind of looks like the reverse of this, where the data is flowing on the other direction. So A transposes become A's, and the multiplication order becomes the opposite. So you're getting G layers gradients, and you're given the alt layer gradients, and you're trying to learn the L minus first layer of gradients. So that's, I don't know why I keep getting these things. Back again. I see no questions, which is good. And in the symbol describes you all these things. Don't get discouraged by it. I'm going to explain whatever is needed. A is a sparse matrix that represents the graph. H is the embeddings that we have defined, just like shown is here, dense, tall, skinny matrix. W is a very small matrix that is F by F, which is the feature by feature length. And it can be different when you're transferring between layers. And G is the derivatives of H, so it's the same size as H, different shape, potentially. And that's all. So in code, it looks like this. You go forward iteration. We apply the formulas we just showed in the previous slide. In the backward iteration, you go backwards in your layers and apply the formulas we have shown in the previous slide. And the big takeaway here is the time is spent doing this following operation. Sparse matrix represents the graph times the tall, skinny, dense matrix that represents the current state of embeddings or feature vectors, you call it, times this mixing matrix W, the learnable matrix W that you use to mix, share across different nodes. And you might parenthesize this differently, or you might just do all of them at once, totally fine. But know that the cost of the dense matrix multiply is much smaller at the end than, let's say you parenthesize it from left to right, then you do sparse matrix times tall, skinny, dense matrix. Well, you get a dense matrix, intermediate matrix, and you will multiply that with the W. The cost of that second multiplication is significantly smaller than the first sparse matrix multiply because of the size of W, how small it is. So the time is spent in doing the SPMM, sparse matrix times dense matrix. And remember from communication avoiding algorithms lecture that you can slice this computational cube of matrix multiply in essentially three main ways, which are 1.5D, 2D, and 3D. And there's an interpolation between them, which are the transitions between these are 1.5D, 2.5D that are between these, in between these two algorithms. So what does that mean? Well, we can think of two different classes of these algorithms for this problem, at least initially. We actually considered all classes of these algorithms. I'm just going to show 1.5D and 2D. And the 1.5D simply is well, let's actually talk about 2D first. You divide both the sparse matrix A and the tall, skinny, dense matrices. Here are depicted as B and C, but in the previous slide, it can be H and W or G. So don't worry about this. Just A is the sparse one and B and C are the dense ones. You can divide all of them in 2D. This will give you an algorithm that looks like a SUMA algorithm that Jim talked about, except that one of the matrices will be sparse. And so it will involve broadcasting A and B, and the owner will compute and update this output matrix C. So that will be memory optimal. We call it stationary C 2D algorithm because the owner computes, so the C stays stationary. The alternative is what's really used, for example, in the NMF calculation in alternating updates framework in the dimensionality reduction part of the lectures, where the now A is 2D decomposed, but B is 1D and C is 1D. So the computation keeps A stationary and moves B around. So how can you do that? You can gather along the processor column of all the slices of B. As the owner of A that is depicted in this blue box, I need not only just my piece, which is the blue part of B, I also need the gray pieces. So how can I get it from respective owners? I can call a gather operation on the processor column. And in fact, what I need to do is an all gather because my neighbors along the column, processor column, will need the same set of embeddings from B, the same. So I'll do an all gather along columns. And once I do my local multiplication, I need to somehow project it back to the output. And that's done by a reduce scatter because I need to reduce my updates with the updates from other processes in my process row. And then I need to scatter it such that the data is not replicated at the output. Though temporarily, I am replicating data. Why? Because I need to all gather these embeddings, and temporarily I'm going to be holding more data than I need. And this is the factor of C, more data. Now the process grid is divided by P over C by C. So temporarily I'm going to be using C times more memory. But in general, I'll be getting better arithmetic intensity if you do the math. There's a 3D algorithm that you can employ in addition to 1.5D and the 2D algorithms we described. And the 3D algorithm we use is awfully similar to the 2D algorithm, except that now different parts of the output are computed by different process layers. Maybe this is a little too much for this lecture, given that what I already have talked to you about. So this is, I'm going to skip these details and just move into what you get when you parallelize SPMM in the graph convolutional network training. You get bandwidth, latency, and memory numbers as shown in this slide. The trick here to see is the 1.5D algorithm is clearly better than the 1D algorithm because you get this denominator C, and in the 1D algorithm, there is no denominator that is anything to do with the processor count. The 2D algorithm seems to be also not bad. It also has nice stuff in the denominator. The trouble with the 2D algorithm is its constants are high and its arithmetic intensity is going to be lower. And for that, you have to read the paper. And 3D algorithm further lowers the communication by increasing the denominator in the bandwidth term to p to the 2/3 at the expense of even higher constants in the NF part, not in the sparse matrix part. Will that pay off? We'll see. So if you run this thing in one GPU and a node, and I believe this is going to be the only thing I'm going to talk about today, you do actually get performance that is predicted by the analysis, meaning as we increase C, which is the replication factor, so C equals 1 is a 1D algorithm, C equals 2 is a 1.5D algorithm with C equals 2, and then more, you get actually better speed up. If we didn't do this and we kept C constant and tried to run 1D algorithm on these data sets, we'll see that we will see no scaling. We would get a, in fact, the runtime on 100 node is higher. But if we use actually increasing C and choose the optimal C for each process count, we can actually see scaling. I believe C equals 4 is didn't run, that's why it doesn't exist. So choosing with larger C as the problem size increases usually pays off. And here's one little wrinkle you can see, like in 64 processes, you probably want to choose C equals 2, or maybe this is just noise. But in 100 processes, you want to increase C, and that's consistent with the theory that you're replicating more because you have more memory. You can replicate more and get lower communication. I think I don't want to talk more about the particular details. There's a couple more unique aspects of the summit that makes this scaling harder, but I will actually remove these slides or mark them as irrelevant so that the people who are downloading this know that they're not responsible for those parts in the quizzes. The summary is graph representation learning is transforming science, and we can solve cool deep learning problems with GNNs. And there's the open work of distributed sampling for mini batch training. That's just the summary of the GNN part. In general, the summary of today's lectures is that we've covered unsupervised learning and semi-supervised learning with graph neural networks. And we covered within unsupervised learning clustering, dimensionality reduction, and embeddings. Most of those boil down into computational primitives that are required to solve these problems that often involve sparse matrix computations. So that's the end of the lecture. Thank you for bearing with me. This is a significant update from last year's lecture. So there's a lot of new material here. You can ask more about any unclear parts on Piazza.